Hello, hello. There he is. There he is. There she is. There he is. There.
Morning, Professor.
Good morning. Thank you for saying so. Good morning. And good morning. So good morning, Brandon. Good morning, Colin. Good morning, Alexis. This, the quorum.
Morning.
Good morning. Good morning, Xavier. Good morning, Xavier. The quorum, the think tank, the Mensa. Good morning, Charlene. Good morning, Anissa. Sorry. Good morning, Gaia. Good morning, Michaela. Good morning, Adenelsi. Good morning, Ryan. Good morning, Carolina. Good morning, Alexis for the double. All right, we got who else? Carolina. Oh my God, that thing is intense. Okay, well, okay. So we can just move on here in the material, which is amazing. So we're going to proceed to the next homework, believe it or not. So now we're moving. Wait, no, we're not. We're going to let somebody in. Okay, we're going to proceed to start talking about homework five. Yes, homework five. Which will push us for, well, first of all, homework five will take advantage of our new knowledge, our new knowledge that if and only if the acceleration of an object is constant, then the average velocity for the whole motion, the average velocity between 2 points in space and time, is the same as the instantaneous velocity at the middle of the time. That's what we're saying so far, which then means in equation form, the first equation. So what this says on the board right here, right? If and only if A equals A naught, like if and only if the rate at which a velocity is changing is not changing, right? If we're having an unchanging change, that's what we're talking about here. If that is the case, that you're gaining or losing velocity at a steady rate, then and only then, first equation on the board here, then and only then, the average velocity for the whole segment between 2 points will be the same value as the instantaneous velocity at the middle point in time, right? Which then means, as this equation is saying, and again, this goes back to what someone said in the direct chat yesterday. With that first equation, then wait, sorry. And what I just said, like in English, again, okay, so shortcut. I'm saying the median and the mean average do not mean the same thing. They are not the same concept. Adding a bunch of things together and dividing by the number of numbers is not the same concept as finding the middle number. And they often are not the same number, right? But as long as numbers, particularly velocity numbers, are changing at a constant rate, then the median, the mean for the whole thing will be the same as the median value, the value right in the middle. And what now that's English. That is still English, right? What that really means for us, before I say the equation thing, in English, what that really means, and this is like the major insight, is like we had just gotten through, particularly in two videos that you watched, like trying to emphasize that the average for a segment between 2 points does not mean the same thing as the value at any given point in that segment, right? Like your average in a class is not the same thing as what you got on any individual exam or assignment or whatever, right? They just aren't the same. And so any equation that we had gotten up until this point, particularly average velocity is defined to be displacement over time. One emphasis we're trying to make is that you can't use that equation to find out how fast something is going at a moment. Like people do all the time, but then they get things wrong. You cannot just infer how fast something is going at a moment from knowing what it's doing on average. But now this equation here, number one, in the middle of the board right here, says, well, you can, as long as acceleration's constant. So constant acceleration is like a big advantage in problem solving. If acceleration's constant, you actually can transfer your knowledge of the whole segment, your average approximate knowledge. You can convert that into exact knowledge of what's going on at a moment, as long as acceleration is constant. And the way you do that, and this is again, now this is the part, this is what the equation says. And like everything I just said is not obvious from that equation. Please know again, I will move on in a moment. But please know that we're now entering the realm of double equal sign equations. They are vaguer in a way than triple equal sign equations, right? Like all the information implied by this discovery of this double equal sign equation, it's not like all explicit whenever you use it to plug and chug. So everything I just said, I don't know that it's explicitly clear in that equation, but it's true. And the part of that the equation is making explicit, V bar equals V naught plus V over 2. What's explicitly saying is, oh, so if you want to know the average velocity for a whole segment, when velocity is changing continuously, like even when the velocity is different at every single moment, as long as the velocity is changing in a constant way, then what you can do is literally just take the lowest velocity and the highest velocity, or whatever, the first and the last velocity, add them together and divide by 2. And that will be the average for the whole. Like it's a major number of steps to skip, and it's a major breakthrough. And notice in that first equation, among other things, what we're saying is then you don't need to know the time at all to figure out average velocity, right? That's a first time we're saying that in this class. Like up until now, I've been screaming and screaming, like average velocity is displacement over time. Like that's, don't sit around just like averaging velocities to get average velocity. Average velocity is displacement over time, right? That's the definition. That was the point of the Hill figure problem in the Grandma Grimm problem. But now we're saying, oh, okay, but that's all true. But if there is acceleration, but it's constant, then actually you can totally end run the time. And as long as you know the lowest velocity and the highest velocity, whatever, as long as you know the first velocity and the last velocity, if they are changing at a constant rate, then you could just add them together and divide by 2, which again is like what people sort of wanted to do in the first place in the Hill figure problem, right? Like 40 and 60 megabit, right? So, but we're saying you can do that. You can eliminate all the intermediary values and just add the first and the last and divide by 2, like literally it's saying just average them, right? As long and only if acceleration is constant. So again, I'm going to move on. But I'm saying it is a mathematical thing. Yes, it's a plug and chug. Like, yes, you can use that equation in a big way, and we do all the time. But often what we're using it for is to get average velocity. Well, to get average velocity when we don't know the time. But B, also what we're using it for is we're saying once we get that average, this is the part where I'm going to say now again, you might want to write this down because this is not obvious in the equation. It's only obvious, it's only like evident if you follow all the logic behind the equation. So I'm saying, first of all, yes, you can use that first equation to find average velocity even when you don't know the time, right? That's like the practical use of it. But second of all, I'm saying once you use that equation when you're allowed to, uh, then not only do you have the average velocity, but you tacitly have the instantaneous velocity right at the middle. And that allows you, once you have that, and if you know the acceleration rate, then you can know any instantaneous velocity like anywhere else in the problem. I mean, in the experiment, in the situation. So, I mean, I can't emphasize this enough. What you don't know by just plugging into that equation or just looking at it, what is not obvious but is so important is that equation allows you to convert your knowledge of the whole segment between 2 points into knowledge of a particular point in time and space. That's really why it's so important. Okay, so we'll practice that, right? Now, the second thing, we're going to go on to the homework, to homework 5. But homework 5 like makes use of that even in places where you don't It's definitely a GDP, a step three for problem solving. Like you don't always, one of those things when you don't know what to think or you don't know what to do, don't forget about this equation. Consider it. It's often the missing piece when you're missing pieces. The other thing that will allow me to now to segue to homework five, you'll see that there's another equation written directly underneath number one, right? Like I haven't said anything. You may recognize it from high school, but I haven't said anything about it yet. Sorry. It doesn't help that I like scream so much. It doesn't help anybody. It helps me stay awake. Uh, the second equation I is a goal for the class. Like I'll get to it today, and I'll break it down for you. But sorry. Sorry. Okay. I'm looking at direct chat. You got. Okay. Yeah. So the number two on the okay. But really, what I want to say before I like start talking about homework five or that equation, the key thing on the board right now is notice how it says if and only if A equals A naught, and then like writes two equations underneath it. One you already know, one you don't know yet. What you really want to infer from this board is okay, now we're in the realm of constant acceleration. Like first we learned about velocity and all that. We had all this like different ways of looking at velocity, and hopefully you see there's average velocity, there's instantaneous velocity. Then we sidebar, which isn't really a sidebar, to Galileo's principle of relativity and realize, oh my God, velocity, like there's instantaneous, there's average. And not only that, it's velocity is relative to a frame of reference. Like velocity is like a deep concept. It's not, it could be one number if it's me looking at the world, and it's a different number if it's you looking at the world, assuming one of us is moving at a different speed from the other, right? So there's like a lot of implications about velocity. Then we move on to acceleration, which is change in velocity per time, right? Okay, so acceleration is change in velocity. Now we're in the realm of physics where we're going to look at, okay, what implications can we draw from when the acceleration that exists does not change? Like that becomes a big topic now. It turns out that when there's a change in velocity, but there's no change in that, in other words, calculus wise, we're now saying from here on in, when there's a second derivative of position with respect to time, but there's no third derivative, or like not no third derivative, but when the third derivative is zero, we're in a so if you understand calculus or calculator, whatever, you're putting together the calculus in your mind, we're now in a realm where we're saying we're interested in situations where the second derivative of position with respect to time is something, is a number, but it's a number, it's a constant. So the third derivative, the derivative of it, is zero. That's literally where physics like focuses a lot of attention. On derivative number two, not derivative number one, and not derivative number three. And derivatives, if you understand them, like you can keep taking them forever in your mind. Like they go on, the concept of a derivative goes on forever. But we're seeing in physics, derivative number two is special. And we'll find out more details why it's special. But the main reason it's special is it's the one you feel. Like literally, the whole point, not the whole point, but a big point of the train of thought experiment is that you don't feel motion, right? Whether it's that smooth train or an airplane or like planet Earth, you don't feel velocity. And you can't like prove that it's there or whatever. Like you can like you can't like velocity. To those of you who are criminalists, to those of you who are solving crimes, which is like in a way almost all of you, right? The velocity does not leave a trace. Like literally, there's no evidence of velocity, like ever. But acceleration does. Acceleration leaves a trace. I mean, you feel it. And more to this, and I really mean you feel it. Like you'll ultimately see in this class, if you didn't already put this together in your mind, like when the airplane takes off or turns intensely enough or lands intensely enough, like not only do you feel it in your stomach, but you might feel it in the contact between your body and the seat. And if the acceleration is intense enough, the seat might even, or the tray table might bruise you. I'm not being silly. I mean, it sounds like I'm not trying to be silly. Like acceleration can literally leave a trace, like evidence, like there was acceleration that just occurred. And it doesn't matter what your perspective is, you would like have to agree that acceleration just occurred. But that's not true of velocity. So we now study acceleration. And but we study the simplest case of it that we can first, the case of acceleration that opens up a lot of implications, and that's the case of constant acceleration. So that's what like so this like next homework and the next one is like all about. And free fall is the most natural, commonly occurring example of constant acceleration. That's really what Lab 3 was meant to show. Even though I know it's like a very ass backwards way of showing that, when I get a chance, I'll try to explain why it explains that. Wait, put in the chat. I'm going to keep going. Put in the chat. I'm assuming you've already had to hand in your lab reports for Lab 3. If you have not, I might be able to help with that. But I assume since you're up to Lab 4 that you're already done with lab. So tell me in the chat, are you done with lab reports for Lab 3? But I'll keep going while I wait for the chat. But Lab 3 was supposed to show you that acceleration in free fall is a constant. And then Lab 4, you're like making use of that constant. You're like already assuming it by Lab 4. So I'm gonna switch. But could someone put in the chat like wait, okay, I'm gonna switch screens to show you where I'm talking about in the homework. So we're going to the homework now. But it's all bottom line, it's all about constant acceleration, unchanging change. So the homework, here we are. Okay, wait. But yeah, and I was hoping, okay, thank you for first of all for paying attention. I see in the direct chat. Yeah, I do. So wait, so thank you. So I see some things in the direct chat. I'm asking the lab with the cookie sheet and the bolts on a string, which I know is a very strange. I mean, I love the lab. I don't, I mean, I wrote, I mean, but I'm defensive because I know it's like really weird while you're, hopefully it's fun and not hard while you're doing it. But then when you're trying to figure out what the heck it taught you, I know that's difficult. Um, oh, it was Lab 2. Oh, I'm sorry. That's why I'm confusing everybody. Right, it's Lab 2, of course, because Lab 3 is the vectors. Oh my God. Right. And we haven't talked at all about Lab 2. I'm sorry. Jeez. Right. Okay. So I meant Lab 2. So wait, so you did turn that one in. Okay. I'm sorry. So Lab 3 you haven't turned in yet, but and I will, of course I'll get to that. But all right, good reminder. So I have a lot to tell you. All right, I'm just going to move on, going back to them. So I apologize. You've had to be you're always allowed. You are allowed at any moment. I mean, you can always just like say in the middle of the class, like, we're struggling with lab reports right now. Can you help us? Like, you can do that. And even if we're not up, and then it'll also just force me to accelerate with the material, like, no joke. Now I'm not going to do it now because I feel like I've just like talked myself into a hole, but I'll bear in mind that you have not done reports yet on the vector lab, on the piece of paper lab. I'll bear that in mind and try to circle back to that. But you get okay. 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 I'm looking at the chat. Okay. No, fair enough. And I apologize. Right. The free fall was Lab 2. Yeah. Uh, yeah. Okay. Thank you. Yes. Ooh. Okay. Yeah. Yeah, I don't know how I may just like end up being not helpful with Lab 3, but for sure, I think everything I'm going to say here will end up definitely helping you with the report for Lab 4. And yes, you're right. The person who just pointed out, oh my God. Uh, oh my God, yes, Lab 4 is very much related to the duck homework, which comes next. Yeah, good call. So all right, so the ducky, yes. So okay, so I'm going to share screen. Okay, so this is what I'm talking about now. Um, all right. I'm going to do the same thing I did yesterday. I'm going to try. I'm going to just try to like say some answers and I can't always do, sometimes we're just going to have homeworks where I just don't end up going over all of it. Like you notice, we don't really have a recitation in this class, like whatever. I have to make judgments. So what I'm going to do right now is I'm going to just try to say the answers, even, and maybe I'll even skip some for one, and I'm going to try not to over talk about it. And what I want to get to is like two. Oh, and three. Oh, this is not as long as it used to be. Okay. Okay. So, but stop me. If I talk fast, it's because I'm worried about boring you. You can always stop me. So number one, particle starts out from rest, initial velocity 0 with an acceleration of 4 meters per second per second. That you can write that as 4 meters per second squared from now on. You can, and I will. I'm just trying to emphasize there what we were talking about yesterday that like you shouldn't think of squared time as some weirdo thing. It just means that. Um, but do notice the whole key of this problem is now we're talking about constant acceleration. A equals A naught. So anything we've ever said about that will apply here. Okay, what's the particle's instantaneous velocity at t equals 0? Well, it's 0. We just told you. V naught equals 0. We were just told that. What's its instantaneous velocity at t equals 0.5 seconds? It's 2 meters per second, right? And again, stop me if you, or just stop me if you need me to repeat. But V, not V bar and not V naught, V equals 2 meters per second at B, right? Now, I'm going to go on to say, like, okay, first of all, you might ask, wait, what equation did I use to do that? The only equation I'm using to do any of these, like in my head, is A bar triple equal sign V minus V naught over T. I'm just using the definition of average acceleration. That's what I'm using. A bar triple equal sign V minus V naught over T, right? But two things. One, that is a statement of the definition of average acceleration. But I know the average acceleration because they told me the constant acceleration, like the acceleration is never changing. So it's like always 4. So that is the average acceleration. I hope that's clear. But if it's not, let me know. But the other thing is, that's the equation I'm using. Like that's the definition. But in my mind, I'm rearranging it. Like what I'm really saying is if A bar equals V minus V naught over T, well, then V minus V naught equals AT. And therefore, V at any given moment, instantaneous velocity at any given moment equals AT plus V naught. I'm going to say that again. I believe that at any given moment, V equals AT plus V naught. And that's what I'm doing in my head. Okay. Now, should you memorize that? No. I mean, like what I just said is a step 4, not a step 3. Like the step 3 GDP is A bar triple equal sign V minus V naught over T. Like that is the meaning of average acceleration. But then I can do algebra and rearrange it to fit like what I'm trying to figure out in the particular problem and do that. That is step 4. Oh, I think there's things happening in the chat. Oh, I'll look in the chat in one second. Right. I want to emphasize, right? And I'm saying that for your benefit. I do that all the time. Don't think that there's a million different physics equations to memorize. Don't memorize. I mean, if you accidentally do, fine. But don't like try to sit and memorize V equals AT plus V naught. That's not a thing. It's just a result. It's an application of okay, see what I'm saying? And V naught here is 0, right? So it's like, so that's why I can do it in my head. I'm just and, yeah, I'm gonna look in the chat. The chat will save me. Okay. Hold on. Wait a minute. Ooh, would it have been would it have been valid to take the integral of acceleration to end up with like 4t plus c and then just plugging in time there? Whoa, yes. That's awesome. Yeah. That is not a coincidence. No. So someone just like asked, could they do the integral and then end up with like 4t plus c and then plug in the time there? And then they were just like, wait, it worked out, but it, like, did I do too much? Okay. Oh my God. Medicine to my soul and definitely submit for points. Like, that's completely correct. And that is not a coincidence. If you understand that integrating acceleration gets you velocity, oh, does that make me happy? And it's totally true. And it's not a coincidence. And it's not like it's too much. It actually, it might be too much for you to redo that every single time on every exercise in the sheet. Like that might be unnecessary for you. But doing it once is great for you and for me. And it's not a coincidence. It's the real concept that acceleration is the derivative of velocity. Therefore, velocity is the integral of acceleration. Oh, yes, with respect to time. And it's great. And especially say this were an exam. say this for an exam. Anybody who would do that, like at the beginning of the exam and show me, oh, you're gathering up so much points by doing that, you're giving yourself a little bit of a break for later in the exam. Like, I want you to know the reward doesn't just go, it's not just for the afterlife. Like, the more you can really make these connections and explain things at the beginnings of documents, such as exams, it actually gives you more leeway later in the exam to say less. And frankly, even when you're struggling later in the exam on other things like you don't understand as well, it gives you a cushion to for that to happen. Like, it's not wasted effort on your part at all. And frankly, it'll also make it easier for you to do other parts of the exam. So no, that is great, and it's true. And the plus C for the, and I know we're different stages of calculus, different ones of us, but if you do the indefinite integral, you'll get a plus C. That's right. But it turns out what that plus C is V naught. I mean, this is a whole discussion we'll go deep on in physics 204, but the arbitrary constant of integration in math is always a boundary condition, an initial condition of physics. In other words, that plus C there refers to, it comes up because you did an indefinite integral because you didn't not that you did anything wrong, you didn't do anything wrong. But I mean, if we just write it as an indefinite integral, so we don't specify the boundaries, we don't say from this value to that value, then we end up with like a plus C. But what the plus C represents is the values at the beginning and the end that we didn't specify, i.e. the V naught. Like, and the reason you got away with it, not the reason you did it right, even though you didn't like know what the plus C is, I'm assuming you just sort of treated the plus C as zero, because like, what else are you going to do? And you're right to do that because V naught is zero. I'm getting a little excited. No, that's very exciting. And I hope some people got something out of that. Right. No, right. No. You okay? Great. I'm just looking at the chat and I'm going to move on. But yeah, whoa, that's awesome. Yeah. Oh my God, there's so much self-deprecating going on here too. But no, I'm not even going to make jokes. Like the more you guys can see the connection between the derivatives and the integrals and all that, you're also practicing for yourself for physics 204. I promise you, it is not wasted effort. It makes it all clearer. And yes, if then in the rest of the document you go like see above, that's not lazy. That's science. Like that's what you should do. I'll just leave it at that. But no, that's great. That's great. Okay. But I'm going to keep going with the answers. But now I'm also going to say this too, conceptually. Okay. You can tell, all of you, you can tell. If there's one thing I believe is that this crap makes sense, or not even that, because I mean, that's in the eye of the beholder. I mean, I believe that physics is meant to make sense. I even believe that about math. I believe that it often doesn't feel that way to people. I know that. And that included me at times in certain contexts of physics. But it's meant to make sense. And I'm telling you this, the reason that I keep saying that over and over is that when you're trying to make sense of it, when you're trying to do homework or exams, you will have more success if you make the assumption, if you take the leap of faith that there is sense to be made. You don't do well in physics if you just keep trying to, and I'm not saying the person in direct, I'm just saying in general, what skills of memorization and knowledge accumulation that are really important and that we do build up in some other science classes, like they don't serve us as well in physics. What serves us well is to believe that somehow there's a logic to all this that is accessible to us. And the more we assume there's a logic there, the more we actually can take leaps and try steps that we wouldn't otherwise have tried. What that could be calculus for some of us, but for others of us, at least right now at this stage, let me say another way quickly before I go on. When I say in part B, in part B, when I say that the answer um is 2 meters per second. Okay, like I'm really doing that in my head, right? I mean, but if you want to see it on paper, yeah, what I'm doing is saying V equals AT plus V naught. And I'm plugging in for I'll look in the chat in 1 second, sorry. And I'm plugging in 4 for A, and I'm plugging in 1/2 second for T, and I'm plugging in 0 for V naught, right? And so I'm getting 2. But like, how am I doing that in my head? Because I'm a genius? No, I'm not a genius. I'm doing it in my head because I'm not literally doing that in my head. What I'm saying is two things. First of all, if something's constant acceleration, that means it's true everywhere, even at the fractional intervals of time, right? Like part of what this problem is trying to emphasize is like once you understand it's constant acceleration, that means there's no slice of time that you could pick that is too small to capture this change. Right, like it applies down to the half second, quarter second, whatever. That's number one. But number two, I'm saying when I say V equals AT plus V naught, that may sound like a new equation to some of you people. It may even sound unfair, but I'm saying it's just the logic of acceleration. I'm literally saying, why am I screaming? I don't know. I'm literally saying that you all know this if you don't think of it as school or physics or whatever. I mean, and some of you do already get it. I know that too. Maybe most of you already get it. But I'm saying literally, if I told you that you were gaining 4 apples a day in your like that you were just like accumulating or whatever, $4 a day every day because of your job, that you get $4 a day every day and you just started your job today. So you started with no money in your pocket, but you're going to make $4 a day every day from your job, right? If and today you have none. If I asked you how many dollars would you have in your pocket in a half day, you would know that the answer is $2, right? Like that. I mean, that's all I'm saying. And that's all that equation says. Okay, whatever. I'm going to go, wait, but there's something in the chat, or I think wait, did someone just remove something from the chat? Can that even happen? Okay, well, I guess they did. There was something in the chat and then there isn't. I didn't even know you could do that. Okay. That's scary. That'd be like deleting a Bitmoji from a text thread. Okay. So next one, what's the instantaneous velocity at 1? I believe it's 4. What's the next one? D. What's the instantaneous velocity at 1.5? I believe it's 6. What's the instantaneous velocity at t equals 2? I believe it's 8, like v equals 8, right? You see what I'm doing? It's just a pattern. What's the instantaneous velocity at t equals 10? I believe it's 40. And you understand if the thing started off not from rest, if it started off at 5 meters per second, I would literally just add 5 meters per second to all my answers. That's what I mean by saying v equals at plus v naught. Um, okay. G, what's the instant? But stop me if it. Oh, there is something in the chat. Wait. Oh no. Oh, okay. That was the. Oh, okay. Good to know you could do that. No, that's great. But thank you for it. So you can submit that for points, person. And these are different people in the chat, just so you know too. And I really appreciate that. Like it's not all one person. I mean, anyway. That's G. So G, I believe is 80. Yeah, 80 meters per second, right? Okay. Then H, draw a neat, careful scale graph of instantaneous velocity with respect to time, right? So what's this? So first of all, what do we mean when we say graph in physics? We don't mean you have to plot every single point. We don't. I mean, you could do this like on Excel or Desmos or something if you want, but we're not generally expecting that in a homework. We're looking for 3 things in a graph or an exam. We're looking for 3 things in a physics graph generally. One, labeled axes for sure. The axes have to be labeled. Like, what are they and what units of measurement are they in? Right? So you got to have labeled axes with units of measurement. So, like time, seconds, instantaneous velocity, meters per second. And I literally mean that. Like, time is the independent variable and instantaneous velocity is the dependent variable, right? Okay, so seconds, meters per second. So that's one thing you need is labeled axes. The number 2 thing you need is the shape or the trend of the graph. And that usually should be a simple continuous shape that you could literally just draw without a million dots or without a full scatter plot. Uh, I think in this case, it is a straight line. And it's a straight line that is going up and to the right. Yeah, it's a straight line. I mean, assuming that we've labeled like that this is positive and that's it's a straight line that's going up. Uh, and the third, and I'll say one more thing about that in a moment, but the third thing that you usually, well, no, I will say it. It's a straight line that has a slope of 4. Four, right? And now stop me if you don't buy this or you don't see this. It should be a straight line with a slope of 4. And when I say 4, I literally mean the rise over the run is 4. What's the rise measured in? Meters per second. What's the run measured in? Seconds. So it's literally like for every 1 second that the graph goes over, it goes up 4 meters per second. Like that's what acceleration means, right? Like the slope of this graph should be the acceleration because it's the rate of change of velocity with respect to time. I mean, ultimately, it's the derivative. So it should be a straight line with slope 4. And then the third thing that should always be on any graph, besides labeled axes and shape, the third thing, there should be at least 1 point that is labeled like one, like not a million, like 1 point that is labeled to explicate the scale of the graph. Like, because so now we have a shape, we know it, we have a relationship, we know what the relationship is between two quantities, and then we label 1 point so that we can see the scale of the relationship. So the 1 point that I might measure, that I often would label is a y-intercept. And I believe in this case, the y-intercept is 0, right? So the whole graph is a straight line of slope 4 coming from the origin. What just, okay, sorry, something just happened, but not interesting. So I think that's all you have to provide, and that's what it is. And I want you to, right? I mean, and the reason so in short, just like the slope of a position time graph would be, sorry, the slope between 2 points on a position time graph would be average velocity. So whenever, right, no matter what kind of graph it is. So that means that at a point on a position time graph, the slope of the tangent line is instantaneous velocity. Right. Hopefully that's clear. So in other words, if a position time graph is straight, then that means the velocity is constant. Well, all that applies by analogy. If the slope between any 2 points on a velocity time graph would be average acceleration, the slope at a point, the slope of the tangent line to a point on a velocity time graph would be instantaneous acceleration. And if the slope is constant, if the velocity time graph is a straight line, then the acceleration is constant. That's what I'm saying. I'm going to move on unless you don't want me to. But I hope it's clear that if it had asked, and it didn't, if it had asked for a position time graph of all these facts, that would not be a straight line, right? Like that would be concave up, like parabolic, like quadrat. I hope that, right, it could be going faster and faster. I hope that's clear. And that's sort of the essence of lab 2. But okay. All right, stop me. So what's the average velocity? Okay. Well, let me just turn. My God. What's the average velocity between during the first 2 seconds of the trip? The average velocity is during the first 2 seconds, it's just the average velocity is 4. What's the average, right? Well, maybe I should, well, I think the answer is 4. During the first 2 seconds of the trip, I think the average velocity is 4. And some of you might have gotten that wrong. And I want some honesty here. I'll go on, but like it's not 8, it's 4 for the first 2 seconds of the trip. Right? Because this now starts to relate back to what we said yesterday. Like the instantaneous velocity at t equals 2 seconds is 8. But therefore, the average for the first 2 seconds is 4. You should really stop me if you have any question about that, because we're going to use that in a big way and like in the rest of it. But okay, but if you don't, so it's 4. And then what's the average velocity for the entire 20-second trip? Well, I I believe it's 40 meters per second for the entire trip. Like it's not 80, right? And it's not 0, it's 40 for the whole. That's the average velocity. In other words, the instantaneous velocity at the middle of the trip. Like that's the concept from yesterday. But I'm going to go on. And honestly, partly because I really trust this class and really like this class. Like I feel like you guys really do tell me stuff. Okay, so I'm moving on, if that's clear. All right. So now we're going to get to the next one where it gets a little bit more interesting. It's 11:30. Okay. We're getting to the next one. A bicycle is at rest and it accelerates at a constant rate of 2 meters per second squared. How far does it travel in the first? Oh, there is something in the chat. I'm almost relieved. Hold on. Oh, it's clear. Oh, it's clear. Thank you. Awesome. Great. Thank you. And that is points for you can move on or whatever. Please go forward. Please submit to that portal that's called Please Go Forward person. And for the record to everybody, that person that just said it's clear is a totally different person from the other people that were in the chat before. I'm just saying. So thank you. Okay. So this next one, I almost want to add. Oh, yes. Thank you for your honesty. Now, this is a totally different person. Thank you for your honesty. Someone is saying in the chat, could I go over J? Okay, I will right now, and I'm not going to distract. And I'm going to say it like once or whatever, but then I'm going to end up saying this same concept again, like when we go to this bicycle thing. So in J, well, equation wise, like it's asking for average velocity. So the equation I'm using in my head is that new one that was on the board, like that came from yesterday. The equation I'm using is the double equal sign is V bar, V bar, double equal sign equals V naught plus V over 2. That's the equation I'm using. So I'm saying the average velocity for this whole thing, because I don't know anything about, well, I mean, I do actually know. Well, because even though I know about time in J, they tell me the whole 20-second trip, so I know about time. But what I don't know is the displacement. Like, I don't know how far it got. So I'm thinking, is there any other equation that, like, if I'm thinking equation wise, uh, yes, there is a different equation I can use since I don't know the displacement. I could say V bar equals V naught plus V over 2. And the reason I can use that one is because I was specifically told that the acceleration is constant. So like I can't use this one when acceleration is not constant, but it is. So I'm saying V bar equals V naught plus V over 2. And I'm saying, well, what's V naught? Well, it's 0. Like the very first velocity of this whole thing, I was told was 0. And what's the very final velocity for this whole thing for 20 seconds? Well, I found it out in part G. I found out that it was 80. So I'm literally. So did I give the wrong answer for J? Is that what's happening here? Well, I don't remember what I said, but here's what I'm saying now that's correct. Like I'm literally saying 0 plus 80 divided by 2 is 40. And if that's not what I said before, I apologize. No wonder you're asking, and I don't know why you're the only person if that's not what I said before. But I'm saying 40 because I'm saying it's the oh no, that is what I said before. Because it's the average of 0 and 80. Like 80 is how fast we got to right at the end, right in the last instant, we got up to a speed of 80. And right at the beginning, we were going 0. And we were speeding up continually the whole time, like the whole time. So on average, we were going the middle value between those two, 0 plus 80 divided by 2, 40. That's my answer. That's how I got 40. Um, what I do, but that's important enough, and especially because now I don't remember if that's what I said before. Could you please tell me in the chat, person who just asked me that, does that clarify? Hello. Wait. Does that the person who just asked me to go over J, please let me know if that is helps? Or if not, I'm going to go on. Yes. Okay. Great. Great. Thank you. And that you get points for that for closing a conversational path. Okay. Thank you. Awesome. Um, now, notice everybody. I'm moving on to the bicycle. Notice one thing they never asked you here is how far how far the particle got, like ever. It never asks you how far, because that's a harder question. I mean, well, we could, and that's what we're sort of about to find practice in this bicycle thing. And in fact, I will loop back and ask you about the particle once we see it in the bicycle. But notice that is a next level question. This is a pattern of how velocities are changing in time, then how displacements are changing or positions are changing based on that really is like a question of integration, like the other direct chat person was saying. So anyway, this one, I'm going to ask you right now. Wait, it's 11:35. I'm going to ask you right now in the direct chat, like all of you, look at the question right here on the board. Like most of you did your homework. But whether you have your homework in front of you now, like whether you did it right or wrong, or whether you have it in front of you right now or not, we've been talking about this enough. I want you to look Oh, it even says, oh, it even says the answer is not 2 meters. Okay, I guess that's not, but okay, it says the answer is not 2 meters, but okay, well, all right. No, actually, forget the direct chat thing because it's not going to be as useful value of time as I thought. Okay, so the answer is not. So you have a bicycle. It's at rest. It's accelerating at a constant rate of 2 meters per second squared. We want to know how far does it travel in the first second. Bottom line, I think the answer is 1 second. 1 second, and I think that you need to stay with me, and I'm going to apply that like that's and I will eventually show how that leads to this next equation that we have and that you might remember from high school. But I want you to see first that you can understand that without plugging in to an equation like 1 f AT squared or anything. And you can do it without calculus. Like, yes, you can use calculus, but I want you to see conceptually that the bicycle only goes 1 meter in the first second. Oh, chat, already chat. Wait, no, sorry, that's what I mean to say. The answer is 1 meter. I'm sorry, I'm sorry. Wait. Oh, sorry. No, sorry. Wait. No, the answer is 1 meter. The answer is 1 meter, not 1 second. The answer is 1 meter. It's not 2 meters and it's not 1 second. It's 1 meter. And if you do get that, or well, sorry. 1 meter, 1 meter. Yeah. A lot of people in the chat. Okay. Well, you really are paying attention, that's for sure. 1 meter. So, okay, wait, you know what? Then I think a lot of people do understand that. I want you to see that you could do there's more in the chat. Wait. Don't scare you. Sorry, I'm not trying to scare you. You say don't scare me, but like, look at that. Look at like Carolina's avatar, for heaven's sake. And I'm saying this with respect, kind of the kind of respect that comes from fear. Like, I don't need to scare you. Look at that avatar. But okay, okay. I'm glad. Thank you, Carolina, for accepting that. Okay, so I don't want to waste your time since a lot of you seem to have gotten it right, but it is like really important. So let's just do this quickly. What I'm going to ask you in the chat is based on that, based on that. Now, could you ultimately use like 1 f AT squared or whatever? Sure. And am I going to teach that? Yes. But I submit to you, physics makes sense. Like 1 f AT squared is true because this stuff makes sense, not the other way around. This stuff doesn't make sense because of 1 f AT squared. So pretend for a minute. I mean, and maybe so you don't know 1 f AT squared yet, as far as I'm concerned. Like we haven't done the Google search. We didn't go to high school, whatever. So I want you to look back at problem one, all of you. This is going to be a direct chat thing. Look at problem one. And without doing any squares or anything, I want you to tell me, I'll write this. Well, can I write this down? I don't know if I could. I'll write in the chat. I want you to tell me, everybody, in direct chat. Hold on, I'll put it in the chat. How can I? Sorry. Okay, so the question in direct chat that I want you to answer, it's not wasn't homework, it is now. I mean, it's a do now. Um, that particle at the fifth second, by the fifth second, how far has it gone? That's what I want to know. Yeah, that's what I want to know. And I want you to put all of you, and if nothing else in the direct chat, put something like, I understand the question, but I cannot answer it, or like whatever, just acknowledge somehow in the direct chat. And again, you could all submit for points, but I'm asking, especially those of you who like do all your homework and like are ahead, I'm at like, don't just plug into 1 f AT squared. Like, don't. I'm not saying that's not true, but I'm saying so that we can see if we really understand this, okay? And because I haven't taught that yet, so whatever. Okay, but why? I gotta get and I'm gonna yeah, and I'm gonna stop the screen share because it's driving me crazy. Hold on. Okay. 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 And I'm seeing answers in the chat, which is good. I'm seeing answers in the chat, and notice, and I'm going to give you another hint, and they're good. I'm, and they're all different. So you are participating. Thank you. You're understanding the question. Thank you. I'm getting a lot of different answers, so I do not think this is a waste of your time. I think this is, in fact, just requiring enough thought that it's worth it. I'm going to, and there's some honesty in there too in the chat. I'm going to remind you one thing. Whatever your answer is, I'm asking how far has the particle gone at 5 seconds? So whatever your answer is, it should have units, but the units should be meters. And that's not just a technical point. That could help, it might suggest to you, if you got something in meters per second, don't just cross them out and call them meters. If you got something in meters per second, that might suggest that you haven't really got solved for the right thing. So I'm going to pause for a second more, and I'm also going to put on the other board. Ooh. Now I'm not going to type out responses to every direct chat because that won't be efficient, but okay, great. I'm going to I'm going to read out please give me a little bit more. If you haven't said anything, please say something. Okay, wow. So I'm getting at least one of these answers is correct. I can also tell you that. I can even tell you, no, I can't tell you more. One of these answers is correct. I'm going to start reading them out loud, but keep them coming. I got 20 meters per second. Which then the person corrected to me, but I got 20 meters per second. Then I got 10 meters. Then I got 20 meters per second squared. Then I got 20 meters per second. Now, again, obviously, I gave the hint wait, you want to be thinking in meters, I think. Then I got one. I don't know. Fair enough. Then I want to say 20, but I could be severely wrong. Then I got 20 meters. Okay, that's certainly less than severely wrong. Then, sorry, 1 meter. Okay, that's a correction. That's good. That's an improvement. Then I got, oh, wait, then 50 meters. Then I got, I understand the question, but don't know how to solve it. Totally fair. I totally appreciate that is helpful. Then I got 2.5 meters. Then I got 100 meters. Then I got 20 meters. So, okay, now then I got 10 meters, not sure. Appreciate the honesty, fair enough. All of you should submit for points. And if you got it wrong, you could submit to the wrong portal as well. Of course, I'm going to tell you in a second, but I think hopefully you'll see even from all these different answers that this is worth paying attention to now. This is not a sidebar. I hope that's clear. One thing I'm going to say before I say the answer or before I say how to do it, I think it's very interesting that at least one person, once I told you to watch your units, at least one person, when they changed their units, actually got a different number. That is awesome. Whether the number is right or wrong, the fact that once you looked at units, then it literally changed your answer, meaning it literally changed your thought process, that's being a true scientist. If you, right, knowing that the units are not just some technical thing that you just change the detail to make the teacher happy, right? Okay, so I'm just saying, and in fact, I'll even say, oh, that's fine. No, and some people are saying they're wrong. Yeah, although I am asking you to do it without squaring anything. Some people now I'm seeing are plugging into an equation that is correct. I'm not saying it's not correct, but my ultimate goal is to show you why the equation is correct and where it came from, that it isn't just a memorizing thing. So I believe, in other words, that all of you have enough knowledge now, if you're following the class. We know enough to solve this problem without a fancy equation. The equation is a shortcut to use in the future to capture understanding that we do have access to now. And that's like why people believe in the equation. You see what I'm saying? So try to do this without, and especially again, because like I don't want to be unfair to you. I can't ask you guys to use an equation that I haven't taught yet, but I can ask you to figure things out that I haven't taught you because that's the whole nature of physics is that we figure things out. Anyway, so try to do it without that equation. And again, it goes both ways. You can always assume at any time that whatever I'm asking you to do in this class, I'm asking you to think hard and push the envelope further. But I'm not asking you to know things that we do. I'm not assuming that you know things that like we don't know yet, if that makes sense. So okay. So I'm gonna well, all right. I'm gonna switch boards and try to move on. Wait, is this the whole homework? Well, this is great actually, because yeah, it means we will. And the last thing I'm going to say right now, even if it doesn't look like I explicitly get, the very last problem homework, the practice proof, it looks like it's out of nowhere, but it's really, it's really just showing you how we put together equations that we already have to make a new equation. So with this final equation that we're going to land on today, that some of you are like sort of already using, what I'm trying to encourage you to see, or what we will, is that that is not new knowledge, not new information. It is just a shortcut packaging of information that we already have. So we don't actually literally ever need it. It whatever. So that's what so you'll see that. That's what or we will be finished with this homework when class is over today. Hold on. So good. Hold on. Hold on. Hold on. I'm just there was one of the. But if I did happen to tell anybody who's right, like there's a lot of different answers here. So a couple of them are right. If yeah. So if I told you you're right, keep it to yourself for a minute, kind of. Um. Okay. So here's what I'm going to do. Okay. Hold on. Hold on. Sharing screen. Sharing. Right. So this is the problem that I've just like I gave you the information from problem number one, but I'm like asking a new question, which is at t equals 5, what's x? Now, yes, I understand that you could just plug in to an equation that I've not developed yet, but or you could be logical about it and use the equations that we already have. So I think that, well, just say, I think the answer is 50 meters. 50 meters. Now I'm going to say it once like in English, and I'm going to use the equations in English. This is why I think so. And I think you can do this in your head. I mean, I think I did it, and I think you can do this in your head. I think that at t equals 5, at t equals 5, I believe that the instantaneous velocity is 20 meters per second, right? This is right. Like if I just asked that as an exercise, you would have gotten that right. Like I'm doing this a little bit fast, but right. And the units do work. I guess I should do this. right? It's 4 meters per second squared times 5 seconds. So one of the seconds cancels out. You get meters per second. Like the units do work. And you get B equals 20 meters per second. Now, what is that? That is not the answer to the whole question. That is close. Oh, very good. I'm seeing the chat. Oh, okay. I see something in the chat that's not bad. That's public. Not bad. Let me be. Oh, I'm going to slow that down a little. The question though is where'd you get that 10 from though? Like, why is that 10 true? So this is but good, and definitely submit for points. Here's what I'm saying. At the end of the 5th second, at the moment of t equals 5, the particle is going instantaneously 20 meters per second, right? There's no bar over my v. That is how fast instantaneously the thing is going at the 5th second. But therefore, on average, for the first 5 seconds, right? On average, it was going 0 plus 20 meters per second divided by 2, 10 meters per second. So in effect, boom. Okay, so it is what Maria, yes. It's totally the yesy thing that Maria has in the chat. Like for real, it's not a coincidence. Like, right? The average velocity this thing was doing for those 5 seconds, on average, it was traveling 10 meters per second. Therefore, its displacement, let's even do it even better. Its displacement was average velocity times time, right? Was 10 meters per second times 5 seconds, 50 meters. Now, right? Now, you might even say, wait, where'd you get that from, Yaverbound? What x minus x naught equals v over t? Well, first of all, distance equals rate times time, right? I mean, how fast you went on average times time is how far you went. But much more to the point, that is just a rearrangement again of what that is just the definition of average velocity. Average velocity is displacement per time, therefore multiply both sides by t. Displacement is average velocity times time. But right? So it always like physics. I'm sure many of you might be, oh, wait. Oh, okay, cool, fine. Yes, good person in direct chat. You got to the 10 meters per second, but then you just had to multiply it by 5. I hear you. I see you. What I'm trying to say, this is one of those moments. Many of you, if you're thinking it all like, oh, yeah, it totally makes sense now, then you're either thinking, well, why didn't he say that before? Why didn't he just make it that simple and clear before, meaning me, right? Or you're saying, like, oh, I should have thought of that before. But scratch both of those thoughts. Don't get angry at the past tense version of me, and don't get angry at the past tense version of you. Like, this is the way physics always is. We get like it does make sense. And it will start making more and more sense in the future version of you. Like you'll see it in advance more and more frequently, but you don't start seeing it in advance until you first recognize how much it did make sense in retrospect. I'm saying this. The key insight here, it circles back to like the first assignment of the semester, is that we always knew distance equals rate times time, distance equals rate times time. In a way, all of physics is just an expansion of distance equals rate times time. But the first thing we're saying in physics is like, whoa, what kind of rate? There's lots of kind of rates in physics, right? When you say distance equals rate times time, what you really mean is distance equals average rate of speed times time. Or if you're talking displacement, you mean average rate of velocity times time, right? It's the average that, right? And conversely, if I know, this is the whole thing of being pulled over by the police officer. If I know that I went 60 miles for an hour, for 2 hours, that means on average I was traveling 30 miles an hour. It doesn't mean that I know anything about what I was doing at any given moment. But the flip of that is true. If I want to know how far I went in 2 hours, what physics is saying is what you need to know is not how fast you were going at any given moment, and certainly not, and this is what everybody gets fooled at. If you want to know how far you went for 2 hours, don't ask yourself how fast you were going at the end of the 2 hours. That's what people tacitly accidentally do with these kind of problems. Like this is where don't confuse instantaneous. don't think, oh, well, at the end of 5, I was going 20 meters per second. So I guess I'm going 20 meters per second times 5. No. What you want to know is how fast were you going on average? How fast you were going on average, but now you can get it because we have V naught plus V over 2. Like that is the why that's like a breakthrough for us. So, okay, so that's what I used. I mean, we got 10 minutes left. So what I did, I used I think it just conceptually makes sense. Like, yes, I did it in my head, but I'm not trying to ask you to like suddenly like be a head thinker. Not suddenly, not yet. But I am saying if you want to just be an equation person, fine, but the equations that we already had at this moment are sufficient. They do capture everything that we're saying. You could literally use A bar equals V minus V naught over T, and you could use V bar equals X minus X naught over T, and you put them together and you got this answer. Right now, slay. I don't even know what that means. I mean, I do, but I don't. I mean, I think it's a good thing, I think. So we have 9 minutes left. What the heck does this have to do with anything? Well, the generalization of the oh good, thank you. Okay, so but slay is a good thing, yes, but admitting you don't know what slay is, that's a bad thing. Right, got it. 360 no scope, got it. What does it have to do with anything? It means from now on, like, do you want, as long as you understand how it all connects, do you need to do all those steps from now on every single time? Like, no. Like, from now on, given A equals A naught, if you have some constant acceleration and you know the initial velocity and you know the time, can we just cut to the chase and get like from now on, can we figure out how far something is going as long as we know its rate of acceleration and its initial velocity? Yes, we can. Yes, we can figure out how far, like that's what we just showed ourselves that we can. From now on, if we know how much time something's traveling for at a given rate of acceleration, we could, as long as we know its initial velocity, we can know how far it's going. But notice what we just realized. If the rate that we know is acceleration, you can't say distance equals rate times time then. You can't be like distance equals rate of acceleration times time. If we had done that in this case, we would have said time is 5, rate of acceleration is 4, so it goes 20. And it didn't go to, and a lot of you put that in the chat. It's totally understandable, but it is wrong. This thing in 5 seconds did not go 20 meters. It got up to a speed of 20 meters per second, right? So what do we do to extend that knowledge to bring it back to actual distance? We go like this. What we just did in our heads or with the equations, if I put the equations together, what I'm saying is, sorry, I'm saying we knew this and we, right? Yeah. And we knew this. Sorry, that's a triple equal. And we knew this, right? So in effect, what we did, oh, and we knew this. We literally, in our heads, like put together all these 3 pieces of knowledge to get the answer. So do we need to put them together every single time? No, we could put them together once for all time. We can say, therefore, X minus X naught equals, like we can substitute all of this, all of that in for that and say, okay, X minus X naught equals why am I, yeah. Oh, I see why. I'm sorry. This is, Jesus. Blame it on the chemo, blame it on the chemo, even though that's what I mean to say. I'm sorry. Right. So we can go like this. right? But then we go, so in effect, I said, like, we want the average velocity times the time. The average velocity is the average of the beginning velocity and the final velocity. But I didn't know the final velocity. Fine, I didn't know the velocity at the 5th second, but I figured it out by rearranging this, right? So I can plug in, I can go V naught plus AT plus V naught all over 2 times T. Am I asking you to do this? I am asking you to write this down now. We have 5 minutes. I'm not asking you to redo all of this every time. I'm not. I'm asking you to see that something makes sense. Like what I just was yelling in English was this. I was saying, oh, distance displacement equals average velocity times time. The average velocity is the average of the velocities. Oh, I don't know the final velocity, so I got to get it from the acceleration. So if I had done that all algebraically, that's what I'm doing here. I'm just putting it all together. I'll write on the next. So I have so far x minus x naught equals v naught plus at plus v naught all over uh, 2 all times t, right? And then, so I can collect like terms. I have 2v, no, well, here, I'll do it like, I can collect like terms. I have at plus 2v naught all over 2 times t, right? And then I can't cancel out the twos. Do whatever, however you think about it. Like I can say, in other words, at over 2 plus v naught. Maybe for some of you, I just skipped a step, but if you do it on your piece of paper, you'll see. Yeah, I'm just going to keep going. So then I distribute the t and say at squared over 2 plus v naught t is what? It equals the displacement. And this is that famous, and now you might write it a different way. Like in high school, you might have put the x naught on the other side. And often the x naught is 0. And it was 0 in this case, but it doesn't have to be. Just like in the homework 1 number line, x naught wasn't 0. So that thing right there, first of all, we've got 3 minutes left, right? First of all, I'm saying from now on, you can use that, sure. But I want you to see a couple of things about it. First of all, it's a double equal sign. It is only true. It totally, all it is an algebraic combination of the 3 equations that we had so far, like the 3 non-calculus looking equations. But one of those equations was only true if the acceleration was a constant, right? So first of all, this thing only works when there is a value of a. When there is a value of a, that doesn't change. Second of all it's doing is saying what those equations already said and putting them together. Yes, if you know calculus, another way of looking at this thing is this is what happens if you take 2 derivatives. Sorry. Well, yeah. I mean, this is what happens if you take 2 integrals of a, like one person was doing in the direct chat. Like when that person took a integral to get v, they in effect got the equation that I keep saying, at plus v naught. They got that from an integral. And if you integrated that again, you would get this. That's already interesting. Yeah, combining all forces for this equation. Oh, cool. Right. But then let me also say, since we have 1 more minute, what this equation's really trying to say is what lab 2, in a way, was really trying to say, which is, oh, once you have a change in the change, but no change in that, once you have a second derivative, then position is a second power of time. It's not a coincidence. When you had constant velocity and no acceleration, then position is a linear function of time. It's directly proportional to time. Like you go twice as much time, you go twice as far if it's constant velocity. Now, if it's constant acceleration, it's the distance is not directly proportional to the time. It's directly proportional to the square of the time. That's why the bolts on the string had to be at the perfect squares so that they all landed at the same time, because they're, or put another way, the fact that they were all at the perfect squares worked shows that free fall acceleration is a constant acceleration because the perfect squares on your string worked. That shows that when you fall down, you speed up your speed up, but you don't speed up your speed up, like literally. There's a second derivative, but there ain't no third derivative. So the positions are in the perfect squares of time. That's the point. Now you can use that equation legally. Have a nice day. I will see you Monday. You're all, I love this class. Like seriously. Yeah, I know. I know. I'm sorry. I should have told you this way. That's the way I will, you remind me in the next lab report. Literally when your next lab report is due, whatever I'm doing, I owe it to you to help you more with your next lab report. I will. But oh well. So now you, okay. Fair enough. See you. See you. No, but right. Totes. Okay.